Hi, everybody, and welcome to the first video of Unit 5. This lesson is called Critical Points and Increasing versus Decreasing. We have one learning target for today. The learning target for today is I can use the first derivative of a function, to find information about a function, including the locations of critical points. So we're going to be looking for critical points today, intervals of increasing and intervals of decreasing. Now, before we begin, since this is our first lesson of a new unit, I want to just give you kind of the big picture about where this is going. So in this unit, we will be focusing on how we can use the first derivative and the second derivative to analyze features of a function. And those features include intervals or sections of the graph where the function is increasing, decreasing, concave up, and concave down. So those are all new vocabulary words, as well as the locations of critical points, points of inflection, maximum values, and minimum values. So again, some of those are review vocabulary words. We might know increasing, decreasing, maximum, and minimum already, but critical points, points of inflection, concave up, and concave down are all going to be new things that we're going to find. And even for some of these things that we've heard of before, like increasing, decreasing, maxes, and mins, we're going to be finding them in a new way using derivatives and our mathematical tools that we've been learning in calculus. So what I'd like to start with is a review of how we can find where a function is increasing and decreasing using a graph. So let's talk about increasing. When you hear the word increasing, what you should think is that those are the sections of a graph where it has a positive slope. So on this graph, we would be looking at this section right here, and it kind of stops right there at the very tippy top of that hill, as well as this section of the graph right here, because those would be the increasing sections of the graph. Now, when we name where a function is increasing, we use the x values. So since this function has an arrow at the end here, we say that it goes towards negative infinity as its x value. And then that stops right here when x is -2. So our first interval would be negative infinity, comma, -2. And we're going to put a bracket there because there's a closed circle. It kind of stops right here at the top. The next interval would start from +3 and it would go to the +7. And that would be our other endpoint. And we use the union symbol for like joining two intervals together. So union means and. So it's this first interval and the interval from 3 to 7. Now, if we were going to look for where this function was decreasing, if we think about decreasing on a graph, decreasing is going to be the places where the function has a negative slope. So in this case, the negative slope would be this part, and this part right here. Since you need the x values in order to describe this interval, the first x value would go from where x is -2 to where x is +3. And so we would say -2, comma, +3 is where this graph is decreasing. Now, this is really a review of what you guys have talked about before. We've talked about increasing and decreasing in previous math classes. There is one thing that I want to point out to you, which is that whenever we are looking at intervals that are increasing or decreasing, we're always using closed intervals, meaning we're using brackets on our notation here. The only exception when we don't use a bracket is when there's a negative infinity. So we're always going to use brackets except a positive or a negative infinity because you can't get to the end there, so you can't catch it. You can't capture it with a bracket. Okay, now what we need to do is connect what we already know visually about increasing and decreasing with just saying and describing that as being a positive slope or a negative slope to what we've been talking about with derivatives. So in order to help make that connection, we're going to start by talking about something called critical points. So the next topic here is going to be all about critical points. And this is going to be a new vocabulary term for most of us that we're learning in this unit. What I'd like to do is circle the points on the graph where either the derivative is 0 or does not exist. Now, as a review, the derivative is going to be 0 whenever the slope would be 0, or in other words, there would be a horizontal tangent line, which means if you kind of imagine the tangent line, it would go straight across like this, or does not exist. And as a reminder, a derivative does not exist at a corner, cusp, vertical tangent, or discontinuity. So if I were to circle those points on this graph, all of those points are called critical points. Critical points are the places where the derivative either is equal to 0 or does not exist. On this graph, that would be this point right here, the derivative is equal to 0. This point right here, because there's a corner, I should make a note that this is a point that is a critical point because the slope would be 0. There would be a corner right here, so the derivative would not exist. There would be a slope of 0 right here because the tangent line would be horizontal right here at the bottom. And there would be a derivative that doesn't exist right here because, again, there's a corner, so the derivative doesn't exist. Now, what I want you to notice is that each of the places where the graph changes from increasing to decreasing, so one place would be here and one place would be here, where it changes from increasing to decreasing or vice versa, is a subset of the critical points. So in other words, if you want to find these places without having a graph in front of you, if you find the critical points, then you have found the places where the graph changes from increasing to decreasing. The only issue is you might have some extra values in there. You might have some critical points that are not places where the graph changes from increasing to decreasing. So once you find the critical points, you're going to need to have a second step where you determine if the graph actually changes slopes at those points. Let's talk about how to do that. So here are the steps for analyzing a function to determine critical points increasing and decreasing. We can use derivatives to determine where a function is increasing and decreasing, even when we don't have a graph. Step number 1 is find the critical points. So to do that, you're going to find the derivative, or I'm going to call that y prime for this kind of definition. Then you're going to take the derivative and you're going to set it equal to 0 and solve, because that is one way that we can possibly have a critical point, is it's a place where the derivative is equal to 0. Then you're going to determine any x values for which the derivative is undefined, because that's another way for us to get a critical point, is that either the derivative is 0 or the derivative is undefined. By doing these 3 steps, find the first derivative, set it equal to 0, and determine where it's undefined, we are finding the x values of the critical points. Now, once you find those points, you have found all of the potential places where the graph changes from increasing to decreasing or decreasing to increasing. The trick now is to determine, is the graph increasing or decreasing on each of those intervals? So the next step is going to be to make a number line chart. Your number line chart is going to use your critical points to divide the chart into sections. So if you think back to what we did in the previous problem, where we used the x values along the x-axis to create these intervals, what we're going to be doing is drawing a little mini x-axis and listing those critical points so that we can divide the graph into sections that are either increasing or decreasing. And then to determine whether the graph is increasing or decreasing on each section, we're going to test a value from each section by substituting that value into the first derivative. If the first derivative is greater than or equal to 0, we say that the function is increasing. And if the first derivative is less than or equal to 0, we say that the function is decreasing. And again, that's because greater than or equal to 0 would mean that you have a positive slope, so it's increasing. And less than or equal to 0 would mean that you have a negative slope, so that would be decreasing for that section. Now, as a secondary part of this question, we are often asked to justify our answers. So the problems will usually say, determine the locations of the critical points, justify your answer. Your chart that you make as part of the work here is not a valid justification to explain why a function is increasing or decreasing on a certain interval. In order to justify your answer, you have to actually write a sentence that refers to the function and its derivative. So do not use pronouns. For example, you could write something like this: f of x is increasing on the interval from -2 to 3 because f prime of x is greater than or equal to 0. So you'll notice that we actually use mathematical symbols here, and we do not use pronouns. You're not going to say because it is positive or the graph is uphill. You need to use mathematical terminology. So f prime of x is greater than or equal to 0 would be your reason here. All right, let's go through this process once just to give you an idea of what's happening. Remember, step number 1 is going to be to find the critical points. So that means we're going to find the first derivative. The first derivative here is going to be 6x squared plus 6x equals 0 because we want to find the places where the derivative is equal to 0. Now, if you factor this in order to solve, you're going to have 6x times x plus 1 equals 0. So you're going to get x equals 0 or x equals -1. Now, there are no places where this derivative is undefined. Because this derivative is a polynomial, and so there are no x values that you can't plug in or that would make this derivative undefined. If your derivative ended up having a fraction or a square root in it, there could very well be values that you can't plug in. For example, in a fraction, the denominator cannot be 0. So you do need to think about where your derivative would be undefined. In this case, since there are no x values where the derivative is undefined, we're just going to look at the numbers where the derivative is equal to 0, which would be when x is 0 and x is -1. Now what we're going to do is draw a mini number line. Now remember, this is the second step, is to make a number line chart. So in our mini number line, here's how we're going to do this. The two critical points are 0 and -1. So you want to kind of imagine where those numbers would fall on a number line. 0 would be to the right of the -1. On a number line, the very beginning of the number line would be -infinity, and the very end would be +infinity. So what we're going to do now is turn this idea into a chart. For the purposes of what we're doing, it's going to be much easier. And so this is just to remind you that this is a number line. We're going to write our numbers above the number line. So the beginning of our number line is going to be -infinity, then -1, then 0, then infinity. So it's the same thing, we're just writing the numbers above the number line. Now those numbers are going to become the dividers of this chart, and we're literally going to turn this like into a chart like this, where we've got like a row, and f prime is what we're going to be evaluating here. So we're going to be determining the sign of f prime. Now, in order to do this, we're going to choose a number that lives within each of these sections. So we need to choose a number between -infinity and -1. In between -infinity and -1, an easy number would be like -10. Now, I'm going to plug that number into the factored form of my derivative. And the reason I'm using the factored form is I actually think it's much easier to plug this number in. When you plug in this number, you get 6 times -10, which is a negative number, and then -10 plus 1, which is another negative number. And when you multiply two negatives, you get a positive. So this section of the graph would be increasing, or in other words, it would be going uphill. Then between -1 and 0, we would pick a number like maybe -1/2. If we plug the -1/2 in, 6 times -1/2 would be negative, -1/2 plus 1 would be positive. And if you multiply a negative times a positive, you get a negative number. So this part of the graph would be going downhill. And last but not least, between 0 and infinity, like a number like positive 10, if you were to plug that in, 6 times 10 is positive, and 10 plus 1 is positive. And when you multiply two positives together, you get a positive number. So that part of the graph would be going uphill. Now we've made our sign chart. And by the way, this is just because I wanted to show you guys to think about this as a number line. You don't need to actually do this part. You can jump straight to the chart. So let's see if we can now use this information to answer the questions. Where are the critical points? Where is the graph increasing? And where is the graph decreasing? So let's start with critical points. The critical points are the places where the derivative is equal to 0 or is undefined. So in this case, that would be where x is equal to 0 or negative 1, which I found by solving my derivative equal to 0 equation. And I would say because f prime of x is equal to 0. Now you'll notice I'm using mathematical terminology here because f prime, the derivative, is equal to 0. Increasing is going to be the parts of the graph where the function is going uphill. So we're going to have two parts of the graph where the function's going uphill. The first section where the graph is going uphill is this one, and the second section where the graph is going uphill is this one. And we can tell that because we got positive numbers when we evaluated the sign of our derivative using our chart. So we would say that the first interval goes from negative infinity to negative 1 because those were the x values from the number line. And the second interval goes from 0 to infinity. Now, if we want to list our reason here, we would say because f prime of x is less than or equal to 0. Last but not least, we want to find the sections of the graph that are decreasing. Now, decreasing is going to be downhill. So that's going to be this middle section right here where we got a negative number when we evaluated. So this decreasing section would go from negative 1 to 0. And we would say because f prime of x is less than or equal to 0. You guys, I totally goofed. This should be greater than or equal to 0. I'm so sorry. I'm trying to talk and write at the same time, and I just totally goofed there. So this should be greater than or equal to 0 because increasing is when the slope is positive, and this should be less than or equal to 0 because decreasing is when the slope is negative. Now you'll notice that each of these reasons refers to f prime. Critical points where f prime is equal to 0. Increasing is where f prime of x is greater than or equal to 0. And decreasing is where f prime of x is less than or equal to 0. Okay, now that we've learned what to do when we actually have a function to work with, so we're going to take the derivative, set it equal to 0, or determine where it's undefined. That gives us our critical points. Set up those numbers in a number line, but we can make it more look like a chart to help us this time. And then test a number from each section to determine if the slope is positive or negative. Now let's talk about what we do if we're not given a function. What do we do if we're given the graph of f prime? So a very typical AP question and a very typical calculus idea is that we are going to be given the graph of f prime. So again, the graph of f prime. And we're going to be asked to answer questions about the original function, f of x. Before we go through how we're going to do this, I'd like to compare the graph of the original function with the graph of f prime and see if we can make some connections. So let's start with the critical points. Critical points are going to be places where the derivative is equal to 0 or undefined. On the original function, the critical points of this graph would be right here when x is pi over 2, and right here when x is 3 pi over 2. And the reason that those would be the critical points is because those would be places where the slope is equal to 0. And the reason the slope would be equal to 0 is because if you imagine the tangent line, there's like a horizontal tangent line here, and there's a horizontal tangent line here. Now let's compare that to the x values that correspond. So the same x values, pi over 2 and 3 pi over 2, on the graph of the derivative. If I find where x is pi over 2 here, and 3 pi over 2, what you'll notice is that those are not places where the slope is equal to 0 anymore, those become x-intercepts. So what we usually say is that a function has critical points when the first derivative intersects the x-axis. So in other words, when we have x-intercepts, we would say for this problem that the critical points are at pi over 2 and 3 pi over 2. And our reason is the same. It's because those are the places where the first derivative is equal to 0. It's just that when you're looking at the graph of the first derivative, those are the x-intercepts. Now let's talk about increasing. So if we look at the original graph, it would be increasing over the interval from 0 to pi over 2, and then 3 pi over 2 to 2 pi. If we connect those to the same intervals on the graph of the derivative, 0 to pi over 2 is right here, and 3 pi over 2 to 2 pi is right here. So what you'll notice is that they're not, like on this graph it's going uphill, but these sections are not going uphill. Instead, these are both sections that are above the x-axis. So increasing when you're looking at the graph of the derivative, increasing becomes the parts of the graph that are above the x-axis. So that would be from, in this case, 0 to pi over 2 and 3 pi over 2 to 2 pi. And our reason is the same. It's because the derivative is greater than or equal to 0. It's just that when you're looking at the graph of the derivative, that is going to be the places where you have a graph that's above the x-axis. Now, your decreasing section of this graph would be where it's going downhill, so this middle section. And if you look at the graph of the derivative, that's the part of the graph where it's below the x-axis. So this is going to be the decreasing part of the graph. And what we usually say is that a function f is decreasing when its derivative is negative, which means we need to look for where the derivative is below the x-axis. So in this case, that would be from pi over 2 to 3 pi over 2. And our reason is the same. It's because f prime of x is less than or equal to 0. It's just that this means that we're looking below the x-axis when we're looking at the graph of the derivative. So the graph of the original is uphill when the derivative is above the x-axis. The graph of the original is downhill when the derivative is below the x-axis, and the graph of the original has critical points when the derivative has x-intercepts. Now, here's what's going to happen. We are going to give you graphs of the derivative. So it's really important to read the instructions here. This is the graph of f prime. This is not the original, this is the derivative. And we're going to say, find the critical points, find the increasing, find the decreasing. Critical points are going to be the x-intercepts. So on this graph, it's going to be here and here, which means we would say x equals -1 or +2, and we would say because the derivative, which is what we're looking at here, is equal to 0. Increasing is going to be where the original graph was going uphill. But if you've got the derivative, that becomes the sections of the graph that are above the x-axis. So in this case, we would say from -infinity to -1, and then also from 2 to infinity. And we would say because f prime of x is greater than or equal to 0. Last but not least, if we have decreasing, the original is going downhill when the derivative is below the x-axis. So we would say that this graph is decreasing, or the original function f of x is decreasing when we are from -1 to +2, because f prime of x, which is what we're looking at here, is less than or equal to 0, or in other words, it's below the x-axis. All right, that is it for today. Thank you guys so much for watching, and I'll see you soon for some practice.